In the vastness of the cosmos, there exist many intricate and fascinating bodies of immense power and prowess, objects of such immense proportions that it angers humanity's everlasting pursuit of knowledge because of their annoying curiosity. One of these bastions of wonder include the tiny blinkers in the skies known as stars, or that is what we think they are. In fact, stars are mostly huge balls of ionized plasma that are powered by thermonuclear fusion that occur in the core of stars, for example, like our Sun. Now, what I really want to talk about is the more exotic type of stars that can exist, did exist, or will exist in the universe. And there are a lot, and they are very interesting. But before that, I must indulge upon the most common type of stars in our universe and the most basic type of stars before I move on to the more exotic and cool kind. And the first one on the list is stars like our Sun are main sequence stars, stars which fuse hydrogen nuclei into heavier nuclei such as helium and maybe even lithium, carbon, or oxygen in stars that are much heavier than our Sun. Stars which are in the same mass as our Sun usually just form hydrogen to helium like a normal thermonuclear reaction. This produces sufficient energy for stars like our Sun to stop the inward force of gravity from imploding the star, and thus the star reaches a thermal stability that allows it to maintain its shape and size. Main sequence stars vary in size, luminosity, and color from a tenth to 200 times the mass of the Sun and can live for millions or even billions of years and perhaps even trillions of years depending on the size. Main sequence stars can also be classified in terms of luminosity, how bright an object is. It's a measure of brightness of an object. The hottest and brightest being in the O class and the dimmest being in the M class. Examples of main sequence stars include, of course, our Sun. Other than that, there's the star in the Alpha Centauri system, which is 4.2 light years away from us, called Proxima Centauri. It's a red dwarf star and is the nearest star to us besides the Sun. Fun fact, our Sun may seem yellow to us, but in fact it is actually white because the Sun radiates electromagnetic radiation over all the visible spectrum. So, and thus it appears as white in a vacuum. The only reason we see it as yellow is because the blue light in our atmosphere, scatters the light towards the yellow scale. Now, why does it do this? Because even though the Sun appears white as it does everything as it radiates electromagnetic radiation towards all the visible spectrums, it still is more oriented towards the yellow spectrum, and thus it appears a little yellowish white. And thus, when scattered by when scattered by our atmosphere, it moves more towards the yellow, and thus it appears as yellow to us. But in fact, it's actually just white. I'll give here's what it looks like actually in space. Basically, when a main sequence star starts to get really mad, it starts to bubble up and get fatter. This is because the hydrogen that it uses as fuel in its core starts to run out, and thus the very great gravitational force starts to exert more pressure on the core and starts to convert the converted helium into heavier elements such as carbon, oxygen, or lithium, as I mentioned before. This causes a large amount of energy to be released, and it overcomes the force of gravity, and the star starts to expand to several times its original size, and thus becomes a red giant. It would be more like orange in color than red, but that doesn't matter. The size of the star also matters as well. Stars like our Sun can become red giants, but stars much more massive than our Sun can also become red giants, but they're like in a separate category, which I'll discuss later down the line. Generally, stars less than 8 times the mass of the Sun can become red giants. The Sun will turn into a red giant in about 5 billion years and probably eat the Earth for breakfast. And I know that this is a great concern to you, that the Sun will probably eat the Earth, but you need not worry, because humanity will probably kill itself by then or become a spacefaring species far advanced than we can ever imagine. But extinction is more likely. Alright, this is a short one. After extensive and deep research, by extensive and deep, I mean I looked at a wiki page and understood it via good old ChatGPT. I found another phase that our star will go through, which is the asymptotic giant branch phase. Basically, this is the last stage of the red giant phase, in which the star basically starts to use an unstable hydrogen and helium shell that burns alternatively, producing what little energy the star needs to stay alive for little time longer. Since the core is now inert, this interchangeability is very, very unstable, and thus the star starts to expel its outer layer, and eventually it expels all its outer layer and leaves behind only a white dwarf. And speaking of white dwarfs, that's the next one on this list. I've included these two at the same number because essentially they're the same thing, and not because I'm too lazy to write separate distinctions of these stellar objects. Anyway, when a red giant shits out all its atmosphere due to the increasing pressure of the core, it leaves behind a little tiny white dwarf, about the size of the Earth but like hundreds of times more massive. A teaspoon of it would weigh about more than a truck. Now, a white dwarf emits very little light because it gradually cools down as it has no fuel to produce heat of its own. So it gradually expels all its energy and heat left over from when it was a main sequence star. Now, a white dwarf is unique in the fact that it's made up of degenerate matter. Degenerate matter, in a gist, is matter that exists in extreme forms of pressure. We all know that any particle besides a boson cannot exist in the same quantum state as another particle. So, an electron can't exist in the same position as another electron, as according to the Pauli exclusion principle, at least one quantum number is always different. Extreme pressure starts to make the electrons and other particles become very close to each other. Now, the natural law doesn't like it when shit starts to break down, so they have to make a reaction force. And this reaction force is known as the degeneracy pressure. And in the case of white dwarfs, it's electron degeneracy pressure. White dwarf stars last for a very long time, trillions of years to be exact, which is way more than the age of the universe, currently at 13.8 billion years. After a painfully, excruciatingly long time, the white dwarf cools down enough by expelling all its radiation and energy and becomes a black dwarf. Black dwarfs are the last life cycle of a main sequence star like our sun. Our sun will also transform into a black dwarf star which emits no light, exudes negligible heat, and is at about absolute zero temperatures. Scientists have discovered no black dwarfs because they don't exist. It takes a white dwarf trillions of years to die into a black dwarf, and the universe has only been around for about 13.8 billion years. Knowing the goofy shit the universe starts to spill out, I won't be surprised if scientists find one drifting out there somewhere. Red dwarfs are the smallest main sequence stars, just a fraction of the sun's size and mass. They're also the coolest, in terms of temperature, of course, and appear more orange in color than red. Thermonuclear fusion occurs in a slightly different way in a red dwarf as compared to other main sequence stars. In a red dwarf, since the size is very small, the entirety of the star's area or entirety of the surface of the star is used for thermonuclear fusion, and thus it has a very large hydrogen supply, and it converts that hydrogen supply into helium and uses that energy to last for trillions of years. Yes, trillions of years. Or that's a very long time, longer than the age of the universe currently. For comparison, normal main sequence stars like our sun only use the hydrogen supply in the core. So when the core runs out of hydrogen and converts all of it into helium, it has no energy left, even though it has a hydrogen supply on the surface around the core. But it can't use that because it doesn't work that way. It doesn't work that way. Since the red dwarf is small, the material mixes in with the core's hydrogen supply, and thus it has a lot of hydrogen supply. Also, another thing why it lasts for a long time is because there's less pressure on the core, and thus the fusion rate is very slow. So that's two factors of why red dwarfs last for a very long time. Red dwarfs are the most common type of stars. They make up about 75% of the Milky Way's stellar population. Red dwarfs and low mass orange dwarfs are the most common types of stars that exist in our Milky Way. Fun fact: the sun is an anomaly. Surprisingly enough, the sun is not common. It's a pretty massive star. Most of the solar systems in the Milky Way have have stars less massive than our sun. So we should be very glad that our sun exists, because if the sun was replaced by a red dwarf or any other star, or any of the other common stars, we would be toast, man. Like not like in a burnt sort of way. I mean, like we would not exist. Life wouldn't exist. So we should be glad that the sun exists. It's a cool thing. Brown dwarfs aren't technically stars. They're more massive than planet, but not as quite as massive as stars. Generally, the brown dwarfs have a mass between 13 and 80 times that of Jupiter. They emit almost no visible light, but scientists have discovered some that emit light in the infrared spectrum. Some brown dwarfs form the same way as main sequence stars from gas and dust clumps in nebulae. Others may form like planets from disks of gas and dust around stars. Jupiter, the largest planet in the solar system, could have been a brown dwarf star if it was a little bit more massive. In that way, the solar system could have been a binary star system. You know, thinking about it, it wouldn't be such a good idea. Jupiter could have been a star, but that would be like a fucking wet fart of a star. It would be very, very boring, very boring and bad star. But a star nonetheless, I guess. It's actually better that it's not a star, because it's more interesting as a planet, because it's the largest planet in the solar system. So we should be glad that Jupiter is a failed star, because if it wasn't, then we wouldn't exist. And also another thing is, if you feel bad that you're a failure, just remember that Jupiter was also a failure, and look how interesting it turned out to be. It turned out to be the largest planet in the solar system. So if you fail, remember that it could make for interesting lore. Now that we've covered all the boring stars, I can move on to the more cool and interesting stellar balls. These bad boys are the absolute largest solar objects that we have discovered in our universe. Red supergiants are the late evolutionary stage of very massive stars, 10 to 40 times the size of the sun. They are very luminous and contain the largest stars that we have observed. For example, UY Scuti, Stevenson 218 and Westerhout 49-2, which is right now the largest star we have discovered. The sun is but a dot compared to the size of this behemoth. If placed in the solar system in place of the sun, it would encompass the entirety of Saturn and Jupiter's orbit and almost touch Uranus. Despite the massive size of these stars, they are not very dense. Their density would be less than Earth's atmosphere in some layers. The most interesting thing about these red supergiants, besides their size, of course, is the fact that they are the stars which go supernova. Now, these red supergiants at the end of their lifetimes will eventually explode magnificently, in fact, outshining whole galaxies. This is a supernova, and as I said before, is the single most devastating explosion in the universe. When these stars explode, they leave behind two things: either a very, very dense but small neutron star, or wait for it, drum roll, a black hole.